Zürich to speak on boundaries and Moebius geometry.
Thank you. Thank you very much to the organizers for the possibility to be here at that conference and to give this talk on boundaries and Moebius geometry. So for me, boundaries are in some sense boundaries of hyperbolic spaces. So maybe later I will say more to it. So the ideal boundaries of negatively curved spaces, or maybe later even non-positively curved spaces. And Moebius geometry is for me some kind of metric Moebius geometry. So I want to discuss that a little bit. So let's say we have a set which has at least 3 points or 4 points, and Moebius geometry always, this kind of Moebius geometry has to do with studying 4 points. We know, let's say, metric geometry, you will study distance between 2 points, and in Moebius geometry you will study certain relations between 4 points, and it has to do with some kind of pairings of these 4 points, and there are 4 kind of pairings, 3 kinds of pairings. This pairing, then this pairing, and here the diagonal pairing in that picture. And maybe I give these pairings names. Let's say the first pairing is called A. This is the 1, 2, 3, 4 pairing. B is the 1, 3, 2, 4 pairing, and C is the 1, 4, 2, 3 pairing. And always in the background, in Moebius geometry, you have some kind of invariance. So what happens if you permute the entries in your cross ratio or whatever you have? And to understand that, maybe it's good to have the cross ratio homomorphism, which goes from the symmetric group on 4 elements to the symmetric group on 3 elements. Yeah. So and these are here the permutations of entries, and these are the permutations of the cross pairings. So this group has 24 elements, this group just has 6 elements. So the homomorphism, you can of course easily write down the homomorphism. For example, the kernel consists of the kernel, and the permutations, actually these kind of permutations, 1, 2, 3, 4, if you make, in this and 2, 3, 1, 4, and 1, 3, 2, 4, they go to identity. And for example, let's say the permutation, if you take only you permute 1 and 2, then of course this cross pair doesn't change, so A is fixed, but B and C is interchanged. So for example, like this, and of course you can that always in the background plays a role, this homomorphism between these two symmetric between these two permutation groups. So to describe what I mean by a Moebius structure, I give first an example, the Moebius structure of a symmetric. So first the Moebius structure. So a symmetric for me is just a function which associates to a pair of points a number between 0 and infinity, and could be 0 and infinity, such that it is symmetric, and it's positive in the sense that it is 0 only if the 2 points agree. And these are essentially the 2 conditions, but I allow also 1 point at I allow 1 point at infinity. In Moebius geometry, always it's good to have points at infinity, or 1 point at infinity. There may exist 1 point and now I describe, so I consider quadruples, maybe the regular quadruples, so Q. So 4 points is a regular quadruple if all entries are different. Maybe later we can weaken a little bit this assumption that certain entries can coincide, and I give 3 different definitions of what is 3 different but equivalent definitions of Moebius structures for certain reasons. So the first definition is a classical cross ratio. So the classical cross ratio is, so if you define rho ij, define, let's say, I say distance between xi and xj, then one defines some kind of cross ratio of the tuple as, let's say, rho 1, 3, rho 2, 4, divided by rho 1, 4, rho 2, 3. So everybody knows these kind of cross ratios, but of course it is there's sometimes a dispute what is the right choice, which kind of pairing 1, 3, 2, 4 I write here, because there are 6 different possibilities to write it down. And I think if there is some kind of discussion what is the right one, then one should consider all of them. So we consider cross ratios x theta, where theta is in A, B, C. So one of the 3 cross pairs, and let's say xa of q, that is, I think that's what we have. And of course we have also the inverses. And the inverses of this. These are the 6 different cross ratios. Here I have the notation that xa is in some sense b divided by c, and xb is c divided by a, and so on. So there are relations between these cross ratios. And the relations are the following. that the symmetries with respect to the first definition. The first relation is xa times xb times xc is equal to 1. And the other, what happens if you permute the entries? That you can write down using this cross-ratio homomorphism, that is, so for example, x theta. So the formula looks like that. If you permute the entry, so by some permutation, then you get the cross-ratio 3 pi, this cross-ratio homomorphism of theta of q. And here plus minus 1 plus the signum of p. So that is a transformation formula for this cross-ratio if you permute the entries. So this is one possibility to describe this. So I give another possibility which in some sense I like more, but all these different possibilities have the same value on different kind of value. That is the cross-ratio triple. So this is, you consider a subset of the projective space of the projective plane, namely the subset where all these entries have the same sign. I write they are all positive, yeah? So in projective space maybe they have all the same sign. So this is really a triangle with an affine structure. So you can, in the projective plane, and it's the triangle spent in the, let's say, in one of the, which is spent by the unit vectors. Maybe here in between, and it has a very nice affine structure. And here, for example, is the point 1, 1, 1 in the middle. And the cross-ratio triple is just a map from the regular quadruples into that sigma, which associates these three cross pairings, namely the distances, so these are homogeneous coordinates. So it associates to every quadruple of a point here in that region, and the symmetries, the symmetries here, maybe they are a little bit easier to describe, namely the cross-ratio triple of P of Q is phi P and the cross-ratio triple of Q. Of course, the symmetry group with three elements, the symmetry group S3 operates in an obvious way on this triangle, and that is just the symmetries of this cross-ratio triples which you have. Then there is a third description which is due to Puyano. So he things a little bit, I think about combining both, just writing the first description but in a logarithmic way. So then you don't get a cross ratio but a double difference, but you get essentially, yes, 3 double differences, and you define a space, namely ABC, in R3, the following plane, A plus B plus C is equal to 0. So that is just an affine plane with this standard structure of A2. And for a quadruple Q, you define, it is finally some Gromov product minus the logarithm of rho ij, and you define A of Q. You define now, so in some sense you take the logarithm of the corresponding cross ratio. So that is then a double difference between essentially it is such a double difference, and in a similar way B and C, and you define a map M from the regular points into this L. Q goes to AQ, BQ, CQ. Of course, it's easy to see that all these 3 things are completely equivalent. That is easy to see, but you see different features in the different descriptions. So the advantage of the last description is that you now have an affine, that you have really a linear structure here, that you are really in some sense in a 2-dimensional space. The advantage of the first is of course that you have the cross ratio, which is really a number, and with a number you can more easily compute, but essentially the cross ratio is something which is 2-dimensional. So, and you should also see the 2-dimensional picture in the one or in the other way. So corresponding to that, you can now define what is a sub-Moebius structure. So a sub-Moebius structure maybe I take, you can give 3 definitions, maybe definitions corresponding to 1 is a triple of maps XA, XB, XC from the regular quadruples into 0 infinity, which satisfies these symmetry conditions. Which satisfies this condition. Equivalently, you could say a sub-Moebius structure is a map into this sigma, into this triangle in projective space, which satisfies this symmetry condition. And equivalently, I didn't write down the symmetry conditions here. Equivalently, you can give a 3rd definition. You say that something like that is a sub-Moebius structure, because it's not yet a Moebius structure. So what is important is that the Moebius structure, so that these symmetries I have described, describe the symmetries which has a cross ratio if you consider only 4 points. But there is an additional symmetry for the cross for the Moebius structure coming from a symmetric, namely the so-called co-cycle condition. So the co-cycle condition. So I can write down the co-cycle condition, and that is a condition if you have 5 points. So you have, let's say, alpha, x, y, z, beta. Now you have 5 points. Then I can describe it with the cross ratio. In the classical cross ratio would be xc, alpha, x, y, beta, xc, alpha, y, z, beta is equal to xc, alpha, x, z, beta. So it's completely trivial. So you write down the cross ratio here, then some kind of things cancel, and you get that. It's completely trivial, but something more subtle. A consequence is the following. That a sub-Moebius structure comes from a symmetric. So that's the following observation, which is to Bujano. The sub-Moebius structure comes from a symmetric if and only if it satisfies the co-cycle condition. Actually, if you see the paper of Bujano, you will not realize that as a result. He formulated in a completely different, and for me, not really to understand way, but that is interpretation of it. And in some sense, that means that the Moebius, so that we have now all symmetries, namely the symmetries here and the co-cycle condition, in order that an association to every quadruple, either 3 cross ratios or the cross ratio triple or this logarithmic cross ratio triple, that it comes from a symmetric, that there is really in the background some symmetric row with this kind of property. Actually, one can finally say the following. You choose 3 different points in X, and if you have, and let's assume you have a sub-Moebius structure, and you want to show that it comes from a symmetric, you have to define out of the sub-Moebius structure the symmetric. So you can choose 3 different points, alpha, beta, omega, and then define finally a symmetric. It turns out it's a symmetric which depends on alpha, beta, omega. So, and this is defined So essentially, if you look to the same expression here, it means if I would write down, instead of A, I would write down C, it would just be the case that the co-cycle condition says that this is 1. Yeah? But if I take now the other cross ratio, in this case the cross ratio A, then it really defines some expression which turns out to be a symmetric. So you see, it's very nice to have the interplay also between the different cross ratio at the same time. Actually, the symmetric here is characterized by the fact that these 2 points, alpha, beta, have distance 1, and omega is, for this symmetric, is the point at infinity. So you can reconstruct out of the sub-Moebius structure really a symmetric. Of course, different symmetrics. So in some sense now we can say what a Moebius structure then is. It's some kind of an equivalence class of symmetrics. So we say 2 symmetrics are Moebius equivalent if they define the same Moebius structure. So if they define the same cross ratio or cross ratio triple. So then this gives an equivalence relation on the set of symmetrics on a given set X. And a Moebius structure is just an equivalence class of it. So as usual, for metrics, or for symmetrics, a symmetric is in, as I have defined it at the very beginning, is a quite weak concept. It only is a symmetric positive function. Often one wants something more, that it satisfies some triangle inequality. So maybe I'll write down this hierarchy. So if you have a rho is a symmetric, then beta is rho is a quasimetric. Which means that the distance between any 2 points is, okay, everybody knows what is a quasimetric is. Rho a metric is metric, and maybe in this case I write down also something more extreme. Rho is an ultrametric.
I'm afraid I don't know what a quasimetric is.
That you have a triangle inequality,
Right.
but it means that the xz is smaller equal k. There exists a k, that it's smaller equal k times maximum rho xy rho y. Yeah? So that is a.
I thought that's an ultrametric. Oh, it's got a K in it.
A k, yeah.
I've never seen that before.
Oh, sorry. Okay, I'm sorry. Yeah. Okay, you have some kind of triangle inequality. So, but not a kind of usual triangle inequality. Only this side is smaller equal k times the maximum of the 2 other sides. Metric is the usual triangle. The ultrametric is this with k equal to 1. And so, and one can describe this hierarchy in the sense if you consider as a subset in our triangle in projective space, if you consider the relation between the 3 lengths of the 3 sides, rho xy, rho yz, rho zx. Yeah? So a symmetric means only, so maybe it's easier to describe the other way around, because there are more and more restrictions to that. So what is an ultrametric? Ultrametric means if you consider any 3 points and you could this relation, then actually it is in this y. Yeah, so ultrametric means that it's y. That are exactly the points A, B, C, such that the two larger of them coincide. That is this kind of triangle. So metric, so the usual triangle inequality. So what are the points A, B, C in sigma, so that these 3 points satisfy the triangle inequality? That is just this triangle delta. Here at the boundary there are let's say these points 1, 1, 1, where still triangle inequality, also ultrametric inequality is satisfied. Quasimetric means that you have a weak form of triangle inequality. It means, depending on k, it means something like that. Yeah? That it's inside here, or that there exists a k, means that these 3 numbers stay away from the 3 corner points of this sigma. These are the corner points, the unit vectors. The unit vectors are obviously the vectors where you have no kind of triangle inequality. But if you stay a little bit away from it, then you have at least some quasi-metric inequality. Corresponding to that, we have seen that the cross ratio triple goes into the sigma. We can define kind of different kinds of Moebius structures. So, okay, maybe. So for Moebius structures, so if it comes from a symmetric, then M is called a Moebius structure. And if now the cross ratio triple, so this what we have here is in this Y, then we would call this M an ultrametric Moebius structure. And if this is a metric, then this, because then it means that you have triangle inequality for these cross pairing numbers, these 3 products of entries, that is called a Ptolemaic, and this inequality is called the Ptolemaic inequality. So it's Ptolemaic Moebius structure. And here maybe one could say that is a quasi Ptolemaic Moebius structure. So why do I all these kind of stuff for these Moebius structures? Because the Moebius structures are the canonical structures which arise on the boundary of some hyperbolic spaces. In the very classical case, it's of course well known that the isometries of hyperbolic plane are just the Moebius maps, but it is more general. Maybe I describe it here for so-called cat-1 spaces. But it is can be generalized to Gromov hyperbolic spaces also. So let's say cat-1 means that you have comparison with the hyperbolic space of constant curvature -1. So let's say you have a cat-1 space y and x. That is the boundary at infinity of y. And you take a point O in the interior, and you have 2 points at the boundary. You can define the usual Gromov product of these 2 points at the boundary with respect to that base point. So it's the limit of, so you go here distance t and let's say go distance t 2t minus that and go to infinity. That's the Gromov product, and you define a metric. This was due to Baudon, rho O of xy, which is e to the minus this Gromov product. Actually, Baudon has shown that for cat minus 1 space, that is really a metric at infinity. Of course, the metric very much depends on the base point O, but it is easy to see if we consider another base point O prime, that these two metrics are Moebius equivalent. So, and this means Moebius equivalent, which means they define the same cross ratios, or the same cross ratio triple and so on. So they define the same Moebius structures. So they are in the same equivalence class, and so they define the same Moebius structure. So it's therefore that the boundary at infinity of a cat minus 1 space has really a natural, a canonical Moebius structure. It has not a canonical metric, it has but a canonical Moebius structure. So I think the Moebius structure is what is interesting for these spaces. So actually this Moebius structure is Ptolemaic. This is a Ptolemaic Moebius structure. So in some sense one should see, at least for these, let's say, at least these quasi-Ptolemaic Moebius structures, you have some kind of triangle inequalities. Finally you have triangle inequalities, and you can see that certain metrics, for example this metric alpha, beta, omega, with a point omega at infinity, then satisfies the corresponding so this rho that is then a quasi-metric or metric, or in that case would be an ultrametric. So it is so in some sense the Moebius geometry, so my viewpoint is that the Moebius geometry sits between, in some sense, topology and the metric. So let's say metric geometry. So at the boundary at infinity of a cat minus 1 space, we don't have a canonical metric. We have certain metrics, but different depending on the base point. We have a canonical topology. All these metrics give the same topology, but even all these metrics give the same Moebius structure. So, so it sits in some sense in between the metric structure and topology, and therefore I think it should be also studied individually as an own subject in some sense. And that is not completely done, and I would try to make a little bit of propaganda. So there are, for example, there are some concepts which are concepts in metric geometry, but not concepts in topology, but they are or are not concepts in Moebius geometry. For example, completeness is a concept of metric geometry. You can say when a metric is complete, but for topology it doesn't make sense to speak about completeness. But for example, completeness is also a concept of Moebius geometry, which means if one of these metrics is complete, one of these special metrics with a point of infinity is complete, then also another metric in the same Moebius structure is also complete. So you can define what is a complete Moebius structure. And of course, also some other concepts. For example, the concept of doubling is a typical metric concept, and it's also a Moebius concept. So I want to, of course, in some sense, I want to focus that Moebius geometry should play an important role in itself, and so there should be some kind of very special Moebius spaces which are reference spaces. So let's say in metric geometry you have maybe the spaces of constant curvature. You should also have some very nice classification maybe of some Moebius spaces. So maybe before I do that, I will describe a few concepts which you have in Moebius geometry, which are typical concepts of Moebius geometry. And one concept is the following. It has to do with this kind of co-cycle condition. If you have a Moebius space, so a Moebius space, and you have two distinct points in the Moebius space, then the whole space is in some sense foliated by, maybe I call it spheres between that points. So you can say for two, so let's say alpha and beta are fixed, you can say for two other points, if they are on the same sphere between these 2 points. So you say they are on the same sphere between these 2 points. If this distance times this is equal to that distance times that, which means that some cross ratio is really 1. And this is an equivalence relation. So, so it says if they are on the same sphere and y and z are on the same sphere, then x and y are on the same sphere. So you have an equivalence relation, which comes just from the co-cycle condition. So it means in Moebius geometry, of course you know these kind of picture everywhere. So this is a general picture which you have in Moebius geometry. Then another concept I want to focus on is the concept of a circle. Maybe very classical is that a circle is something Moebius invariant, and I describe what a circle is in general context. A circle may exist, usually it's a very rare object. Does it exist? But one can really define. One can say sigma in a Moebius space. So we now have only a set with a Moebius structure is a circle if and only if I want topologically. So we have on the Moebius space we have, so it's stronger than that, so we have automatically a topology, so that sigma is homeomorphic to S1, and for all, so if we have this sigma and we have 4 points, so for all that the cross ratio triple of Q is in the boundary delta. So I had this picture of this sigma. I call this here delta. That is in this affine picture. The triangle delta is a triangle which is spanned by these midpoints. And this boundary, so are exactly the triple of points where you have equality in the triangle inequality. And that means in this context here that for the corresponding distances you have between the 4 points, you have this distance times it, this distance plus this distance times this is equal to this distance times that. And that is the classical characterization of 4 points on a circle in Euclidean space. Yeah? But you can make it as a definition of a circle in some arbitrary Moebius space. Yeah? So I have what should be very important classical spaces as Moebius spaces, which I said that the boundary at infinity of a cut minus 1 space arises, and what are the most prominent boundaries at infinity of cut minus 1 spaces? That should be the boundaries of the rank 1 symmetric spaces. Yeah? And so the boundaries of rank 1 symmetric spaces and the other rank 1 symmetric spaces, that should be in some sense prominent representatives of with their, let's say, canonical Moebius structure coming as boundary of a cut minus 1 space using this Baudon metric. And so one and it is indeed possible, and I did that together with Thomas Förtsch in that case and with Sergei Buyalo in these other cases, that one can characterize these spaces, these Moebius spaces, in a nice way, purely by Moebius geometry. So, and I don't go into details, but for example, the boundary of hyperbolic space as a Moebius space is characterized just by the property that it's a compact space, and a compact Ptolemaic Moebius space, and through any 3 points there is a circle. So this space can be characterized by the property that there are a lot of so plenty of circles in the space, and circle is a Moebius condition. And there is of course much more complicated but also similar kind of characterization for complex hyperbolic space. In for the boundary of complex hyperbolic space. In the boundary of complex hyperbolic space, you have 2 different types of, I say, circles. So the one are circles, and the other, they are called chains. And at least they are called first by Cartan as chains, and they are both characterized in a Moebius way. So the circles I have characterized here, and chains are characterized in a similar way. I don't go into details. And the circles are just the boundaries at infinity. So if you have a complex hyperbolic space, then you have an interior totally real, totally geodesic planes with constant curvature -1, and you have also the complex planes which curvature equal to -4, and the boundary at infinity of the hyperbolic of the constant curvature of the real planes are the circles, and of the complex planes are the chains. And there's some kind of synthetic characterization, 3 axioms which one can easily describe. Maybe the first axiom given any 2 points, there is a chain between the 2 points and some other 2 other axioms, which characterize in a purely Moebius way the boundary of the complex hyperbolic space. And in a similar way, you can do it also for the other rank 1 symmetric spaces. Maybe because I should. Okay, so maybe that I have. Maybe another fact, which maybe is much more expected, and is, but it's also not completely trivial, is if you have a tree. So maybe in this conference one should at least draw some trees or dendrites or something. And if you have a tree which is also a cut -1 space, then actually the Moebius structure you get at the boundary at infinity is an ultrametric Moebius structure. So it means that the Moebius structure, all cross ratio triples are in that Y. Yeah? And on the other hand, you can say the following, that there is really a 1-to-1 correspondence between trees and ultrametric Moebius structures. You have to have some assumptions, namely the tree has to be geodesically complete. So this means that every geodesic segment in the tree can be extended to a whole geodesic. And so you have in the interior geodesically complete trees, and on the boundary complete ultrametric Moebius structures. So if you have a geodesically complete tree, you get on the boundary a complete ultrametric Moebius structure. And if you have an ultrametric Moebius structure, then there exists up to isometry only one geodesically complete tree, such that this is the boundary at infinity. This is a result I've proved with a student, Jonas Beirer. And maybe at the end, I want only to indicate that this kind of Moebius geometry maybe could also be useful to study some non-positively curved spaces. So here we have really used very strongly this hyperbolicity of the space to get a Moebius structure at infinity. So, but so my student Jonas Beirer, he has developed some kind of Moebius geometry for a certain boundary of a higher rank symmetric space, namely the Furstenberg boundary, of symmetric spaces, symmetric spaces of higher rank. So if you have a symmetric space of higher rank, for example, SL3 divided by SO3, then the Furstenberg boundary is the set of all Y chambers at infinity. So let's say so you have these flats which are separated in Y chambers. At infinity you see these Y chambers at infinity. And the union of these Y chambers at infinity is then the Furstenberg boundary of Y. That is now our space X. And one can identify the Furstenberg boundary as a subset of the usual boundary at infinity just by the center of gravity in each of these Weil chambers. Yeah, you choose in each of these Weil chambers the center of gravity, so you get a subset of the boundary at infinity. So then you can try to imitate the construction of Bourdon for that metric. So if you have, let's say, a point in the interior of the space and you have, let's say, two Weil chambers at infinity, you take these two geodesics to the center point of the Weil chamber. Let's say that is the one Weil chamber, the other, and you define this kind of Gromov product in the usual way. The problem with this Gromov product is, which you see, that, for example, if you would be in a flat and that would be here adjacent Weil chambers, the Gromov product can be infinity, which means that the corresponding rho would be 0. So which means, so this guy, so you can define a symmetric function. So now you define a symmetric function on the Furstenberg boundary, but which is not even a symmetric, because different points can have distance, let's say I say distance, but it's not a distance, 0. And a triangle inequality is completely out of reach. But still, it defines on a lot of pairs, namely on opposite pairs, opposite in the sense of the building structure of the boundary at infinity, it defines really a distance, depending on the point. But this means that you can also define some cross ratio or cross ratio. You can also then prove in a similar way. It's a little bit, in a similar way, that these kind of symmetric function, which is even not a symmetric, the symmetric function is Moebius. So if you have different points in the interior, they define the same kind of cross ratio triple, as long as the cross ratio triple is defined. For example, the regular triples would be the triples, let's say quadruples, quadruples, where all are opposite to each other. Yeah. For example, you can define, so you can define some kind of Moebius structure, which is a little bit different, the generalization of that structure. And in this situation, one can show that this Moebius structure, this pure Moebius structure, also characterizes this Furstenberg boundary and then the symmetric space. For example, you can also say all Moebius maps of this Moebius maps of the Furstenberg boundaries. The Moebius maps of the Furstenberg boundaries are exactly the isometries of this symmetric space. Maybe it's not so surprising, but you can really build up a Moebius geometry for these spaces. So same kind of thinking you can do if you have products, really products of hyperbolic spaces. For example, or let's say you have products of cat minus 1 spaces. Yeah, you have a product of two cat minus 1 spaces you can define on some boundary at infinity, namely on the boundary of Weil chambers at infinity, some kind of analogon to the Furstenberg boundary, some kind of Moebius geometry. So it seems to be that at least under certain other instances, certain nice instances, you can really define a Moebius geometry on the boundary. An infinity, or in some boundary, infinity also in the non-positively curved case. Yeah? Maybe it would be challenging to do something now for, let's say, zero cube complexes or so. Because so here, usually you have on the boundary the Titz geometry, so the Titz building structure, but this Moebius structure is in some sense orthogonal to this Titz distance. Yeah? So I think one should, in these kind of higher rank situations, use both the Moebius, some kind of Moebius structure on a certain other boundary, and the Titz metric on the usual boundary. Okay, maybe I stop there.
Any questions?
Yeah.
Can you describe how the Moebius structure varies under quasi? Like, I mean, okay, so you have the quasi-isometry of hyperbolic spaces. How the Moebius structure on the boundaries behaves?
No, I mean that is not solved. Yeah, that would be. I mean, of course. Often you don't have this nice Moebius structure. You should have some kind of quasi-Moebius structure. Yeah, and in some sense, maybe hope is to deform quasi-Moebius structure under certain instances to Moebius structure, and maybe to approach using that certain deeper conjectures, but there's not much known. Sergei Buyalo has some work done in this direction. Maybe you look there.
Does a Moebius geometry induce a coarse geometry? Does a Moebius geometry like induce a coarse geometry? Do you know?
Okay, in some sense, yeah, maybe in some sense. I agree. Yeah, in some sense, one should study all this course, this quasi, and actually I've done that. But I think then finally I've realized that also the honest Moebius structures in that cases are not really studied. So that maybe was most of my motivation. Of course, I think the most interesting is these kinds of questions: how flexible is the structure, and can you deform something? So, for example, you can show that follows from Mineyev, and also Buyalo has proved that if you have a hyperbolic group, then the boundary at infinity as an honest Ptolemaic Moebius structure, invariant. So that the group operates by Moebius transformation on the boundary at infinity. Yeah. So some work is done in that